In this video, we'll see that when both the domain and codomain of a linear transformation are finite dimensional, then the linear transformation can always be represented as a matrix. However, the matrix representation depends on a choice of basis, and so if you change the basis, then the matrix representation will also change for the same linear transformation. Okay, so first we'll look at how to calculate the matrix representation when we're working with the standard basis of Rn. So if you remember, the standard basis for Rn is just E1 through En, right? So it's 1 in the ith position and 0 in the other coordinates. So here the vectors are written in column form. Well, okay, so basically to obtain the standard matrix for a linear transformation, what you do is you calculate the transformation for each of the individual standard basis vectors and obtain the result from the transformation, and you write the resulting vector as a column vector, right? So you transform E1 and then write it as a column vector, transform E2, write that as a column vector, and so on. And if you take each of these individual column vectors and write them as the columns for a matrix, then this matrix will be the matrix representation for the linear transformation, in the sense that transforming a vector V is the same as matrix multiplication with the matrix A. Okay, so let's see how we do this calculation in an example. So here we have a linear transformation. T of x, y, z is given by 3x minus z in the first coordinate and 2y minus z in the second coordinate. So first, if you notice, as an input it takes 3 coordinates, right? So that means that the domain is R3. And as an output it has 2 coordinates, right? So the codomain is R2. Okay, so we need to transform each of the basis vectors in R3. So we do them one by one, right? So first E1 means transforming 1, 0, 0. Right, so this is x, this is y, this is z. So we just plug it into the transformation and calculate, right? So 3 times 1 is 3, and then this doesn't have an x term, right? So that means that here it's just 0 minus 0, which is 0. So I get the vector 3 comma 0, but we want to write as a column vector, right? So I write it like this. And then we do the same for the other basis vectors, right? So E2 would be the vector 0, 1, 0. And here now y is 1. So the first coordinate is 0. Second coordinate is 2 times 1, which is 2. So this is now the vector 0, 2. And now I transform E3. T of 0, 0, 1. So z is 1, the other coordinates are 0, so this would be negative 2, comma, negative 1. And then now written as a column vector. Okay, so now we put this together. All right, so A as a matrix, right? So first column would be 3, 0. Second column would be 0, 2, and third column would be negative 2, negative 1. Okay, so this is our matrix representation. However, if you compare the matrix representation with the formula for the transformation written in this way, right? So let me first write it in a slightly different form where all the terms are written out, right? So the first is 3x. It doesn't have a y term, so that means that the y coefficient is 0, and then minus 2z. And then the second coordinate doesn't have an x term, right? So that has a coefficient of 0, and it's plus 2y minus z. Right, so as a column vector, the output, the top entry is representing the first coordinate, and then the bottom entry is representing the second coordinate. Right, so if you look at the entries in the first row of the matrix A, it's just exactly the coefficients for the first coordinate here, and then the entries in the second row here are just exactly the coordinates here, 0, 2, negative 1. And the way it works out this way for the standard matrix representation is because when you're transforming the standard basis, right, so one of the coordinates is 1 and the other coordinates are 0, right? So for like example here, 1, 0, 0, x is 1, and so when you plug it in, it just picks out the x coordinates, right? So that's 3, 0, and then this is just the y coordinates, the coefficient of the y, and then this is just the coefficient of the z. So you can quite easily just read it off from the formula here. Here we look at composition of functions. So just like with ordinary functions, we can compose linear transformations. So suppose you have two linear transformations, t1 and t2, where the codomain of t1 is the same as the domain of t2. So you need this requirement because the output vector for t1 becomes the input vector for t2, right? So the vector space should match up. Okay, so if we have these two linear transformations, we can compose t2 with t1, where the domain is the domain of t1 and the codomain is the codomain of t2. And the composition is defined in this way, where given a vector in Rn, we first apply the transformation t1, and then the output of that is then transformed by t2. Right, so in function notation, the order that you apply the linear transformations is inside out, right? So t1 is applied first, and then t2 is applied. Okay, so let's take a look at an example. Right, so here we have t1 from R3 to R2. So this is the same linear transformation from the previous page. And we have a second linear transformation from R2 to R2 given by this function. And we want to calculate the composition of the vector -4, 6, -5. Okay, so as mentioned, right, so you apply the inner function first, right? So I apply t1 to the vector -4, 6, -5. Okay, so I just plug it in for t1. So that's 3 times -4 minus 2 times -5, and then 2y, so that's 2 times 6 minus z, which is -5. So the result of this would be -12 plus 10 is -2, and this is 12 plus 5 is 17. Okay, so the output of t1 is -2 comma 17, and then if I want to calculate the composition, right, so the output of the first transformation was this, so this becomes the input for t2, And then now I plug this in for T2. Right, so what do I get? It's negative 2 plus 2 times 17, 3 times negative 2 minus 17. And so I get negative 2 plus 34 is 32. Negative 6 minus 17 is negative 23. Okay, so this is how you can calculate the composition of two functions. Okay, so now let's see how composition of linear transformations relates to their matrix representation. And it essentially is just given by matrix multiplication, right? So A1 is the matrix representation for T1, A2 is the matrix representation for T2, and then composing T2 with T1 is the same thing as multiplying A2 with A1. And notice that you, from left to right, the order of the transformations is the same as the ordering of the matrices. Okay, so let's take a look at these two transformations here, right? So the matrix for T1. So what is that? It's the same matrix as before, but you can again just read off the coefficients, right? So here's 3x, then 0y, then negative 2z, so 3, 0, negative 2. And then it's 0x, 2y, and minus z, so 0, 2, minus 1. And then the matrix for T2 is it's going to be a 2 by 2 matrix because it's R2 to R2. And again, it can just read off coefficients. So 1 and 2, and then 3 and negative 1. Okay, so the matrix for T2 composed with T1 is going to be A2 times A1. A2 on the left, A1 on the right. So 1, 2, 3, negative 1. And then 3, 0, negative 2, 0, 2, negative 1. So 2 by 2 and then 2 by 3. So it's going to be a 2 by 3 as the result. And then we just do the calculation, right? So this is 3 plus 0 is 3. 0 plus 0, 0 plus 4 is 4. Negative 2 minus 2 is negative 4. 9 plus 0 is 9. 0 minus 2 is negative 2. Negative 6 plus 1 is negative 5. Okay, so that's our matrix for the composition. And so let's check the calculation. Right, so the composition applied to negative 4, 6, negative 5, we've already calculated previously. So using the matrix representation, it should be the same. Right, so 3, 4, negative 4, 9, negative 2, negative 5. And then I want to apply the composition to this input vector, negative 4, 6, negative 5, but as a column. And now, because this matrix is representing the composition, then doing the matrix multiplication here should result in the same result as we've calculated previously. So let's do the calculation. So negative 12 plus 24 is 12, minus 20 is negative 8. something is not right. So let's see. Okay, so negative 12 plus 24 is positive 12. This becomes plus 20 because the two minuses, so 12 plus 20 is 32. And then second entry, so negative 36 minus 12 is negative 48. Negative 48 plus 25 is negative 23, which is the same result we got previously. Right, so this checks out. Okay, so composition just becomes the same as matrix multiplication. Just like composition of linear transformations is related to matrix multiplication, we have that inverse transformations are related to the matrix inverse. So basically a linear transformation that's both one-to-one and onto is invertible. And in this case, the inverse linear transformation, right? So because it's one-to-one and onto, the domain and the codomain have to be the same, right? And then the related matrix will be a square matrix that's invertible. Okay, so let's try to calculate the inverse linear transformation. So here we have this linear transformation, which we can find the associated matrix, right? So the matrix A for T. So I can just read off the coefficients. So 1, 1, 1, negative 1. It's 2 by 2. And clearly you can see that the determinant is negative 2. So it's invertible. Well, that means T is also invertible. So what is A inverse? It's 1 over negative 2. And this becomes minus 1 and then 1. This becomes minus 1. This becomes minus 1. And multiplying, what do we have? 1/2, 1/2, 1/2, negative 1/2. And okay, so if we want to write it back in the form of a formula like this, then T inverse of xy, right, so it's 1/2 x plus 1/2 y, and then 1/2 x minus 1/2 y. Okay, so we've been working with the vector spaces Rn and the standard basis. What if we have non-standard bases and other finite dimensional vector spaces? So we can still find the matrix for the linear transformation still in that case, right? So as long as the domain and the codomain are finite dimensional, and the procedure is essentially the same, except you have to be slightly careful with the bases, right? So you still calculate the transformation for each of the individual basis vectors. However, when you write out the column vector should be written in terms of the basis B prime for the codomain, right? So this is the coordinate vector for the basis B prime, not necessarily what the output calculation comes out to be, right? So you get the output calculation, and then based on the output calculation, you have to write the output in terms of the basis vectors for B prime. So what do I mean by this? So let's go over these examples. So here we have a linear transformation that's essentially the derivative operator, right? So we're looking at spaces of polynomials, and the linear transformation is just to take the derivative of the polynomial. So we want to find a matrix for this linear transformation from P3 to P2 according to the bases for P3 and P2. Right, so we apply the derivative to each of the input basis vectors. So derivative of 1 is 0. Derivative of x is 1. Derivative of x squared is 2x. And derivative of x cubed is 3x squared. Okay, so now we have to write these in terms of the output basis, right? So it's just 1x and x squared, right? So this is 0 times 1 plus 0 times x plus 0 times x squared. Similarly, this is 1 times 1 plus 0x plus 0x squared. And this is 0 times 1 plus 2x plus 0x squared. And this is 0 times 1 plus 0x plus 3x squared. Right, and then so now the coordinate vectors is just taking these coefficients, right? So here is 0, 0, 0. The coordinates here are 1, 0, 0. Coordinates here are 0, 2, 0. Coordinates here are 0, 0, 3. Okay, so now I can put them together to form my matrix A, right? So first is the column 0, 0, 0, then the column 1, 0, 0, then the column 0, 2, 0, then the column 0, 0, 3. So again, what you want to remember is after you transform each of the individual basis vectors, you have to write the output in terms of the basis vectors for B prime. Okay, so here we go back to the vector space R2, but now we're looking at a non-standard basis B prime given by these two vectors. Okay, so again I transform each of the individual basis vectors. So T of 4, 1, that's 8 minus 12 is negative 4, and then 4 minus 5 is negative 1. and I transform the next one, 3 comma 1. So what do I get? 3 minus 5 is negative 2. And then, oops, I plug it into the first one. So 3 comma 1, so 6 minus 12 is negative 6. And then 3 minus 5 is negative 2. Okay, so now, again, I don't want to use these coordinates. I have to write the coordinates in terms of the basis b prime. Right, so you can see, okay, so let's call this v1 and v2. Right, so you can see that this is just negative of v1 plus 0 v2. And you can see that this is a multiple of v2, right? So it's negative 2 v2. So 0 v1 minus 2 v2. And these coefficients are what we use. Right? So it's negative 1, 0, right, in terms of the basis b prime. And this would be 0, negative 2 in terms of the basis b prime. Okay, so we get that a prime is equal to negative 1, 0, 0, negative 2. And so the matrix representation for this basis is a diagonal matrix. So in this situation, when you have a non-standard basis, you can't just obtain the matrix just by reading off the coefficients from the formula here, right? So so it's different from a equals 2, negative 12, 1, negative 5. Right, so this would be the standard representation. However, the two are related, which we'll see in the next section.